This is Thomas Gredig, and today we want to calculate the magnetic field from a wire. So we found out that in the 19th century, early in the 19th century, Ørsted actually did some experiments, and he found out that when you run a current through a wire, there's a magnetic field. And the way he observed that was he put a compass needle nearby, and he saw how the compass needle deviated. And from that deviation, he knew that the current in the wire actually was creating that magnetic field. And you can actually use a compass to find the high current wires behind the wall. So it's an easy way to find those. So what we want to do is we want to calculate the magnetic field outside a wire, a certain distance z away at this location, at this red marked location. And we're going to calculate it in a very structured way that we've already learned and established the method when we did electric fields. And we're going to repeat that now for magnetic fields. And it turns out that once you can master that technique, then you can basically calculate the magnetic field of any object. It doesn't have to look like so. And sometimes it can be calculated analytically, where you get an equation as the solution, and it can be used for any point along this z-axis, and sometimes you have to do the calculation numerically. So in this case, the first thing that we would do, the first step a planner would do to make a good drawing. And so I drew the coordinate system, the x, the y, and the z-axis. And so this is a right-handed coordinate system that we always use in this class. And the way you know it's right-handed is you take your right hand, and so this is x, this is y, and then this is always z, the result. So I can put this, and you can see that x goes into board, y goes up, and c goes to the right. Now you could rotate your hand in any direction, but it would always be a right-handed system. Okay, so the current is running up in this wire, and so you know from the right-hand rule that your thumb points up, the magnetic field curls around this wire. And so that means the magnetic field comes out of the board over there, it comes towards me, and then it goes into the board at this location. So we already know that the magnetic field at this location here points into the board. Another way to look at this is you could write down the Biot-Savart law, which tells you that the magnetic field is given by any charges that move with a velocity v. And so in this case, the velocity of the current, positive charges would go in this direction, electrons would flow in that direction, opposite to the current direction. And so positive charges would move up, so that would be the dl, the same direction as the velocity. And the r vector is the vector that goes from the source that creates that magnetic field to the observer. So we're the observer over here, and this would be the source. So the r vector would be the vector from the source to this location here. This would be the r vector. And so again, if you use a right-hand rule, so dl goes up, cross r. So we have to relocate a little bit. This goes up, cross r, and that means that the magnetic field goes into the board. So everything is consistent using both rules, either this rule where we can see the magnetic field curl around the wire, or we just look at the single charge here, a positive charge that moves up. In this direction, we bend towards r, and that means our thumb points into the direction of the magnetic field. So let's calculate it. The second thing that the researcher does after he writes down the magnetic field created by a single charge, here we would need the magnetic field from a wire. And so this is a single charge, and sorry, the magnetic field from a small current element here. That would be equal to mu naught over 4 pi times the current times dl cross r hat divided by r squared. So that's very similar to this, where we have now lots of charges. Instead of just one, we have a whole bunch of charges, a current in this small element. Now, to integrate at this location the magnetic field, we will have to add up all the elements from all the way down here all the way to the point up there. And so the first thing that we need to know is, what is this r vector? And so the x portion would be 0. The y portion would be minus this location here, so that's minus y. And then we go plus z in the z direction, so that's our r vector. And we can also calculate the r hat vector, which is divided by its magnitude. And so it would be 0 minus y, z divided by y squared plus z squared, and we take the square root. That's the magnitude. OK. So now we have our r hat from the equation. We, of course, know the current. This is the universal constant. We know r squared as well. We also need to know dl. And then we need to know the cross product of those two vectors. So dl points only in the y direction. And it's just a small element in the y direction. So we can write this as delta y, or in this case, I'm going to use dy. So this is just a small element in the y direction. This would be our delta y. So now we can take the cross product. And so we do dl cross r hat. And that would be equal to, so the x component would be equal to this times this. So it would be z times dy minus this times this. That's 0. The y component is this times this minus this times this. That's 0. And the z component is this times this minus this times this. So that's also 0. OK, so now we have that component, and we can now write the integral. So the magnetic field, at least the magnitude of the magnetic field, because the direction we already know points into the x direction. The magnitude of this would be mu naught over 4 pi times the integral. And we would integrate all these small pieces from minus L half to plus L half. And so this is actually just a small piece because we have a small piece there. And so we integrate all those small pieces times the current multiplied by this element here. And we're only going to use the x component here. Z dy divided by r squared. And we also get this factor here in the r hat. Oh, OK, sorry, forgot that here. So we're going to get that, the square root, and then we're going to get the square of that. So that means that we're going to have 3 square roots, so 3 halves here. And so now we need to integrate this here. And you can see that we're going to integrate along the y direction only. So the z is a constant. Current is also a constant. We can take that out. So we can take these two out, and then we have to take the integral of that. So that would be mu naught over 4 pi times I times z divided by nothing. And then we have the integral of dy y squared plus c squared to the 3 halves. And so that turns out to be equal to you could look that up in a table, and that's equal to y over c squared times the square root of y squared plus z squared, evaluated for y equal to plus L half and y equal to minus L half. And so if you put those y values in there, you also see that one of the z's cancels. And what we'll get is mu naught divided by 4 pi times I divided by z. And then we're going to get L half here. L half minus L half. L half minus L half, so that's L half plus L half. So that's going to give us 1L divided by L half squared plus Z squared. So that's the magnetic field from a wire. Often we can use a more simplified version of this. Essentially, and this is the condition under which you will be most frequently be using the magnetic field, if you're very close to the wire. When you're very close to the wire, in that case the wire appears to be very long. L is very long compared to Z, so this factor in here dominates, and this becomes 0. So we have, if we take the square root of, we're just going to have L half here, and so we're going to get a 2 up there, and this is approximately equal to mu naught divided by 4 pi times 2I divided by Z. And so that's the magnetic field of a wire when you're close, when the wire is much, much longer than the distance that you're away. And so the magnetic field, the magnitude of the magnetic field close to a wire is proportional to the current, and the further away you go, the smaller it gets as with distance. It's inversely related. And so this is a very useful quantity. Of course, this quantity will only be useful up to a certain distance. After that, only this equation here will be valid, because this is the exact solution, and this is just an approximated quantity. But it's much easier to compute this quantity, and also to remember for a lot of the homework. This will be sufficient to be used, but you want to remember when this equation is valid. The direction of the magnetic field is also important, and the direction you find using your right hand. And in this case, it points up, so the magnetic field points into the wall at all these locations, and on this side, the magnetic field would point out of the wall. So everywhere on that side, the magnetic field comes out. Everywhere on this side, the magnetic field goes into the board. So the direction you usually find using your right hand.